First of all, welcome you in my class 10. Today we will start first chapter of maths, real numbers. In your previous standard, we have studied about real numbers, irrational numbers, rational numbers, integers, whatever. I think you begin your exploration the world of real numbers and encounter irrational numbers also. We will study on real numbers in this chapter. We will start with two important properties of positive integers. First of all, Euclid's division algorithm, and second one, the fundamental theorem of arithmetic in this chapter. These two very important properties of positive integer. Always remember. In this chapter, we will start from these two properties. First of all, I write heading. Chapter 1. Real numbers. As we discussed before, in this chapter we will study two important properties. First, Euclid's division algorithm, and second, the fundamental theorem of arithmetic. First, we will discuss about Euclid's division algorithm. According to this property, suppose a positive integer a. Suppose a positive integer a can be divided by a positive integer b in such a way that leaves a remainder. Suppose a remainder is q. Q is not remainder, but q is a result. But remainder is r, which is smaller than b. Now I write this Euclid division algorithm by an equation. A can be divided by b. This is the result into q, and this is the remainder. Okay, so where r is equal to or greater than 0 and less than mod b. Okay, clear or not? I repeat. First, we will discuss about Euclid's division algorithm, and then the fundamental theorem of arithmetic. This property says that a positive integer, suppose a positive integer a can be divided by other positive integer b that lives a remainder r that is smaller than b. Understood or not? Euclid's division algorithm says that suppose a positive integer a can be divided by another positive integer b that leaves a remainder r that is smaller than b. Means, look over to here, a can be divided by b in such a way that remainder lives, and remainder is smaller than b. This is remainder, and remainder is equal to or greater than 0 and is equal less than mod b. Okay, yeah, b is not equal to 0. Here b is not equal to 0. Okay, I think you have studied in your previous standard. So equation will be like this. A is equal to b cube plus r, where r is equal to or greater than 0 and less than mod b, where b is not equal to 0. Clear? This is Euclid's division algorithm. Now, second one. The second one means second property, the fundamental theorem of arithmetic. I think you already know about a composite number that can be expressed in a unique way. Which is product of primes, which shows product of primes in a unique way. This factor is the fundamental of theorem of arithmetic. Understood or not? Suppose there is a composite number and it can be expressed as a product of primes in unique way. Yeah, this is the factor of the fundamental theorem of arithmetic. Always begin. Okay. Now I write here second property. The fundamental theorem of arithmetic. A composite number can be expressed by a product of primes in a unique way. Yes, this fact is the fundamental theorem of arithmetic. Yes. Clear? First, we will study about first property, Euclid's division algorithm. Then we will study about second property. Clear? We have discussed about two important properties of positive integers. First property is algorithm of Euclid's division, and second one, the fundamental theorem of arithmetic. Now, explanation. The explanation about the first property. Algorithm of Euclid's division. Actually, algorithm of Euclid's division is a technique to compute the highest common factor of two given positive integers. Suppose there are two positive integers and we will take the highest integers first and then second, but you will have to apply lemma of Euclid's division to continue to compute the highest common factor. Let's see how the algorithm works here by taking an example. Suppose there are two positive integers. Means first integer a is equal to 120 and another positive integer b is equal to 23. Now apply lemma of Euclid's division. Lemma of Euclid's division is A is equal to BQ plus R, where R is equal to or greater than 0 and less than mod B. Understood? So, yeah, always remember A must be greater than B. Okay? Here A greater than B. Don't forget. Now, apply the value in this equation. A is equal to 120, B is equal to 23. Now, Q and R also integers, unique integers, remember. And in these integers, you will put yourself, look over here. 120 is equal to 23. Now recall your table of 23. 23, 1 is a 23, 23, 2 is a 46, 23, 3 is a 69, 23, 4 is a 112, double 12, and sorry, 92, sorry, 23, 4 is a 92, and 23, 5 is a 115. Okay, 115, double 15, 115 is closer to 120. So 23, 5 is a 115. 120 minus 115 is equal to 5. And put the value of 5 in place of R. Okay, so 120 is divided by 23. 23 here, 23 is a divisor. And R, means 5, is remainder. Do your process. Continue until you get remainder 0. So now, second step. Now 23, put the value in place of A here. 23 multiply, sorry, 23 is equal to, now remainder will be divisor in your second step. Remainder will be a divisor in your second step, and put it in place of B. Okay? Now, recall your table 5. 5 1 is a 5, 5 2 is a 10, 5 3 is a 15, 5 2 is a 20, and 5 is a 5. That is a 25. 25 is greater than 23. So 5 was a 20. Okay? So 5 was a 20, and 23 minus 20 is equal to 3. Remainder will be here 3. Okay? Carry on until you get remainder 0. Okay? Now 5 is equal to here 3. 3 2 is a 6, which is greater than 5. So 3 1 is a 3 plus 5 minus 3 is equal to 2. Put the value here 3. Then 2 multiplied by 1 plus 3 minus 2 is equal to 1. Here 2 place 1 here. 1 is a 1, 1 2 is a 2, yeah, plus 0, yeah. We reached in the 0. So we got 0 as remainder, and you have got your HCF of 120 and 23. So HCF of 120, 3 is equal to remainder is 0 and last divisor is your HCF. Okay, clear? So this is a little explanation of algorithm, how algorithm works by applying lemma of Euclid's division. Now listen, A is equal to B Q0 plus R0. This is your first step. Second step, B is equal to R0 Q1 plus R1. This is your second step. Sorry for little late to write here. This is my own method to explain you. First your step is over here. A is equal to B Q0 plus R0, where R0 is equal to or greater than 0 and less than B. Understood or not? Where R0 is equal to or greater than 0 and less than B. Always remember. And over here, B is equal to R0. In your second step, R0 will be a divisor of B. Here B is a divisor of A and R0 is divisor of B. Yeah. In your third step, R0 is equal to R1 Q2 plus R. And so on. Carry on your procedure until you get remainder 0. This is very important technique to get HCF of two given positive integers. Clear? Now jump on our exercise 1.1. Here is question. First, use Euclid's division algorithm to find the HCF of 135 and 225. Here there are 3 sub questions. Before go ahead, recall Euclid's division algorithm. Euclid's division algorithm is a technique to compute the highest common factor of two given positive integers. Understood or not? So, algorithm of Euclid division is used to find out HCF of two positive integers. But remember, don't forget, apply lemma of Euclid division also. Lemma of Euclid division also. Equation is A is equal to B Q 0 plus R0, where R0 is equal to or greater than 0 and less than B. And our procedure will continue until you get remainder 0. By applying this lemma division in our this exercise, and we'll see how the algorithm works. Solution 1. Here (225) is greater than 135, so A is equal to 225 and B is equal to 135. Okay? By applying lemma of Euclid division, now A is equal to B Q plus R. A is equal to 225 is equal to B. We put the value 135 in place of B. Yeah. Now 135 is the divisor of 225. 225 divided by 135. 135, 1 is a 135, 5 minus 5 is equal to 0, and 22 minus 13 is equal to 9. Yeah, so remainder is 90 and result is 1. Okay, 135 plus 90. Okay, and now 90 will be divisor of 135 and 135 will be put here in place of 225. Okay, 135 equal to now 90. Yeah, 135 divided by 90. 135 divided by 90. Yeah, 45. 45 is the divisor of, 45 is the remainder of 135 divided by 90. Yeah, plus 45. Okay, now 90 is equal to 45. 90 divided by 45 equal to 2 plus 0. So we have got here 0, remainder 0. So our process stops here. The remainder is 0, so our process stops here. The divisor is 45 at this stage. At this stage or step. Okay, so HCF of 135 and 225 equal to 45. Okay, clear? Now second one. Here 38,000 220 is greater than 196. That's why A is equal to 38,220. Sorry, yeah, 220, and B is equal to 196. According to this formula, or apply this formula over here, A is equal to BQ plus R, where R is equal to or greater than 0 and less than B. 38220 is equal to B. B, put the value of B in place of B, 196. Yeah. Now divide 38,220 by 196. Yeah. Divide by 196. Focus first 3 digit, and now speak table 196. 196 yeah, 196, one is 196. Now minus 196 from 382. 12 minus 6 is equal to 6. Here is 7. 17 minus 9 is equal to 8. Yeah. And here is 2. 0. Now, go ahead. 196 into 10 is equal to 1960. So, before 10, 9, 196. Sorry. Yeah. 9. 196 into 9 equal to 9 6 54. Yeah. Minus. Yeah. 196. 2, 3, 4, 5. Yeah. Yes. Remainder is 0 over here. $195 and remainder is 0. We have got here 0. So our process stops here. The remainder is 0. So our process stops here. The divisor at this stage is 196. So HCF of 196 38220 is equal to 196. Clear? Yeah. Now third one. Here 867 is greater than 255. So A is equal to 867 and B is equal to 255. By applying lemma of Euclid division, A is equal to B Q plus R, where R is equal to greater than 0 and less than B. A is equal to 867, B is equal to 255, multiply. 867 divided by 255. 867 divided by 255. Minus. Remainder is 102. 255 multiplied by 3 plus 102. 255 right here, and then equal to write 102 over here, and now 255 divided by 102. 255 divided by 102. 102 to the 204. 2. Remainder is 51. Now 102 right here, equal to 51 right here, and 102 divided by 51. 51 to the 102 plus 0. The remainder is 0 at this stage, so our process stops here. The remainder is 0. So our process stops here. The divisor is 51. So HCF of 867 and 255 equal to 51. Clear? And now listen. HCF of two integers. How will you calculate? When you get remainder 0, whatever your stage, divisor will be HCF of two positive integers, which is given in your question. Okay? 45 is the divisor of 90. 196 is the divisor of 38220, and 51 is the divisor of 102. But condition applied. Remainder must be 0 at this stage where the divisor is included. Okay? Write down. Here is our second question. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. This is my showcase also. nothing else. Here, suppose a is an integer, a positive integer, any positive integer, and b is equal to 6. See over here, b is equal to 6, and q is equal to or less than 0. Remember, I write here solution. Let a be any positive integer and b is equal to 6. Now, lemma division or Euclid's algorithm, then Euclid's algorithm, a is equal to 6q plus, don't write 1 here, write r, and q is equal to or greater than 0. Equal to or greater than 0. And r is equal to 0 to 5. 0, 1, 2, 3, 4, 5. Why? Because r is equal to or greater than 0 and less than 6. Recall r is equal to or greater than 0 and less than b, and b is equal to b is equal to 6. So r will greater than r less than 6. Okay, no mistake, sorry. And now putting r equal to 0 to 5, and we will get the value of a. If r equal to 0, then a is equal to 6q plus 0 is equal to 6q. If r is equal to 1, then a is equal to 6q plus 1. If r is equal to 2, then a is equal to 6q plus 2. If r is equal to 5, then a is equal to 6q plus 5. Clear? And now a positive integer can be either even or odd. Look over to here. Six q plus 2, 6q plus 4. Even number, and it is divisible by 2. Here a is equal to 6q plus 2, 6q plus 4. A is equal to q, 6 plus 2, 6 2 plus 4. So A is an even number and divisible by 2. A positive integer, either even or odd. A positive integer can either even or odd. So any positive or integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Clear? Here is our third question. An army contingent of 616 members is to march behind an army band of 32 members in parade. Army contingent of 616 members and army band of 32 members. Yeah. So here we have two groups. A group of 616 members and a group of 32 members. Question is, what is the maximum number of columns in which they can march? The two groups are to march in the same number of columns. Let's find it. Solution. From the question, we have army contingent of 616 members and army band members 32. So HCF of 616 and 32 will give the maximum number member of columns in which they can march. By applying Euclid's algorithm, using Euclid's algorithm, (616) is greater than 32, so A is equal to 616 and B is equal to 32. Now A is equal to BQ plus R, where r is equal to or greater than 0 and less than b. A is equal to 616, b is equal to 32. Yeah, 616 divided by 32. 1 is a 32. Yeah. 32 yeah. No. 32 9 the yeah. Yes. Remainder is 8. Result is 19. 32 into 19 plus 8. Okay? 32 is equal to, write here 8, multiply by 4 plus 0. Yes, remainder is 0. And at this stage, divisor is 8. So, they can march in 8 columns each. The remainder is 0. The divisor is 8. So HCF of 616 32 is equal to 8. So we can say here they can march in 8 columns. Each. Clear? Here our fourth question. Use Euclid's division lemma to show that the square of any positive integer is either of form 3m or 3m plus 1 for some integer m. Use Euclid division lemma to show the square of any positive integer. Suppose a is a positive integer, square of any positive integer. Now I will square is either of form 3m or 3m plus 1. Now right here solution. Let a be any positive integer and b is equal to, look over to here, 3. Or some integer which q is equal to or greater than 0. And R is equal to 0, 1, 2, 1 and 2, because R is equal to or greater than 0 and less than 3. That's why I take here R is equal to 0, 1 and 2. Now A is equal to BQ plus R, where R is equal to or greater than 0 and less than B. If R is equal to 0, then A is equal to B. B is equal to 3. Q plus 0 is equal to 3Q. Yeah. Same. If A is equal to 3Q, sorry, if R is equal to 1, then A is equal to 3Q plus 1. If R is equal to 2, then A is equal to 3Q plus 2. Clear? Now, look over here. That's why A is equal to 3Q. That's why, as per question, square both of sides. A square plus 3Q whole square. That's why A square is equal to 3 square is equal to 9Q square. Okay, that's why A square is equal to 3Q square. You can write like this. Okay, that's why A square is equal to 3, and put the value or use a sign in place of 3Q square m, because of 3Q square is equal to m. Okay. Yeah. As per question, do square both of sides. A square 3Q plus 1 whole square. That's why A square is equal to 3Q square is equal to 9Q square plus 3 to the 6Q plus 1. Yeah, that's why A square is equal to 3Q square plus 2Q plus 1. Yeah, that's why A square is equal to 3, and put the value or put the sign or put the m in place of 3Q square plus 2Q. Okay, as per question, do square both of side. A square 3Q plus 2 all square. That's why A square 3Q square means 9Q square plus 3 to the 6 to the 12 q square, sorry, 12q plus 4. Yeah. Now a square plus 9q square plus 12q plus 3 plus 1, you can write 3 plus 1 or 4 is equal to 3 plus 1. A square is equal to 3q square plus 4q plus 1 plus 1. Yeah. That's why a square is equal to 3m plus 1. Yeah. Put the value m in place of this equation. Here m is some positive integer. Here m is some positive integer, so that we can say that the square of any positive integer is either of form 3m or 3m plus 1. Clear? For some integer m. Yes. Here m is some positive integer, so we can say that the square of any positive integer is either of form 3m or 3m plus 1. Clear? Here is our fifth question. Use Euclid's division lemma to show that the cube of any positive integer is either of form 9m or 9m plus 1 or 9m plus 8. Shall we start here? This question is as well as question number 4, as we discussed before. So it's very easy. Solution. Let A be any positive integer and b is equal to 3 and r is equal to or greater than 0 and less than 3. Okay, so r is equal to 0, 1 and 2. Okay, yeah. R is equal to greater than 0 and less than 3. 3 means is equal to b, and r equal to 0, 1 and 2. Now, using lemma of Euclid's division, A is equal to BQ plus R. A is equal to B. B is equal to 3. Q plus R is equal to 0. That's why A is equal to 3Q. As per question, do cube both of side. A cube is equal to 3 cube. That's why A cube is equal to 27 cube. That's why A cube is equal to 9 3 cube. Okay, that's why A cube is equal to 9m. Okay, here m is an integer. Clear? If r is equal to 1, then a is equal to 3 cube plus 1. Then a cube in bracket 3 cube plus 1 cube. As per question, cube do cube both of side. Okay. Now a cube is equal to, expand this step. How? A plus b, according to this formula, a cube plus b cube plus 3a square b plus 3ab square. That means ab will be common here, and in bracket a plus b. Okay, this is the formula, and put the value. So go to here. A cube means 3 cube. Yeah. (27 cube plus b cube means 1 cube plus 1 plus 3 multiply 3 cube into 1 in bracket a plus b is equal to 3 cube plus 1 is equal to 27 cube plus 1 plus 3 9 3 7 27 q square I write more step 9 q into 3 q plus 1 is equal to 27 q cube plus 1 plus 9 3 27 q square plus 9q. Yeah. Now, as per order, 27q cube plus 27q square plus 9q plus 1. Yeah. 9 will be common here. 3q cube plus 3q square plus q plus 1 is equal to 9m plus 1. Okay, put this sign in place of this question. Okay, here m is an integer. Okay, now third one, if r is equal to 2, then A is equal to 3q plus 2. As per question, do cube both of side. Yeah, a cube is equal to a plus b cube. According to this formula, and 27 cube plus 2 cube is equal to 8 plus 3 into 3 cube into 2 in bracket 3 cube plus 2. Okay, a cube plus b cube plus 3ab into a plus b, okay, is equal to 27 cube plus 8 plus 9 into 2 is equal to 18 cube in bracket 3 cube plus 2. 27 cube plus 8 plus 18 is a 54 cube square plus 18 to the 36 cube. Okay, as per order, 27 cube plus 54 cube square plus 36 cube plus 8. Yeah. Keep common with 9. Three cube plus 6 cube square. 54 divided by 9 is equal to 6 cube square. 27 divided by 9, 3 cube. Plus 36 divided by 9, 4 cube. Plus 8. Okay? 9 and put here m in place of this bracket. 9m plus 8. Look over here. 9m plus 8. 9m plus 1 and 9m. Okay? Here m is an integer. Okay? So we can say that the cube of any positive integer is either of form 9m or 9m plus 1 or 9m plus 8 or some integer m. Clear? In our next part will the second property of the fundamental theorem of arithmetic we will start. Okay, then exercise 1.2. Thank you.